Hey everybody. So we're going to do a quick video on division of polynomials here. This can be a useful strategy in a few different situations. Um, but I'm just going to briefly talk about it and do a couple of examples. But I want to start by first considering division that we're more familiar with. So, for example, if we think about the question, does 8 divide 304, right? And so if we wanted to answer this question, one way we might do it is we have this division algorithm that we've probably all seen, right? And there's a couple, I just kind of want to kind of note what we're doing, right? We're not looking at the whole number 304. We start by looking at just the 3. And what we might note is that 3 is too small for 8. So we have to look at the first two numbers, at the 30. And we think about, we just kind of imagine ourselves, we want to take this 8 to 30 through multiplication, and the closest we can get without going over, we multiply by 3. We end up with 24, right? So 3 times 8 is a positive 24. And then we subtract what we get. So we're multiplying the result by negative. So 30 minus 24 leaves us a 6. And then we bring down our next number. And then we do the same game with this, 64. To get there with an 8, we have 8 times 8 gives us 64. We end up with 0. Okay, so the process I'm just kind of gently commenting on because we're gonna do something similar in a more unfamiliar context. But I also want to note what this result means. There's a couple different ways we can think about this. The fact that 304 divided by 8 is equal to 38, right? We could write this as 304 divided by 8 is equal to 38. But another way to think about this meaning is that 304 is equal to 8 times 38, right? That's what the division algorithm does for us. It finds the number that we multiply 8 by to get 304. Okay, let's do one more. Let's do a similar question with does 5 divide 17? And so we do the same thing. And we see that, oh, if I multiply by 3, I get 15, which is close to 17. We subtract, and we're left with 2. And we're not going to go into decimals here. We're just going to consider this our remainder, right? So at some point, this may have been where you stopped dividing, right? And so the way we think about this, there's two different ways we can think about it. Similar to what we did over here, I can think that 17 is actually let's preserve the order, do it the same way we did here. 7 the first time. 17 divided by 5 is equal to 3 plus 2/5. That's what that remainder is. It might be easier to see when we think about it this way. 17 is equal to 5 times 3 plus 2, right? So both of those are kind of good ways to understand this division algorithm, right? So that's, the same way as before. 8 and 38 were the factors that gave us 304. 5 and 3 are the factors that give us 17, but they can't give us 17 exactly, so we have to do something a little extra. We have this extra 2 we have to account for that we call our remainder, okay? So just going to leave that there, and let's now do something similar with polynomials. So let me scroll down a little. Now we're going to play a similar kind of game, and let's look at the polynomial. Give it a name. F of x is x to the 6th plus x to the 5th minus 3x cubed minus 3x squared minus 3x minus 3. And I want to see if if the linear factor or the degree 1 polynomial y equals x plus 1 divides that. And so we're going to do a very similar kind of game. I have my little division bar, and we'll have in here x to the sixth plus x to the fifth minus 3x cubed minus 3x squared minus 3x minus 3. Right? Yeah, there's a lot of 3's in there. And we'll divide it by x plus 1. Okay? We're going to play a similar kind of game. So I'm looking at this x to the sixth, and I want to find a number or something to multiply x plus 1 by to get x to the sixth, right? And really what we're going to think about is this leading term x. I want to get to x to the sixth multiplying x times something. And of course, that something is going to be x to the fifth. So I multiply x to the fifth times x, I get x to the sixth. Then I got to multiply that by the 1, I get x to the fifth. Now remember what we did in our algorithm up above is we subtract this. So now I'm subtracting. So both of these become negative, and we end up with 0. And just like up above, where we brought the 4 down, we're going to bring our next numbers down, or our next terms down. 3x minus 3x cubed. I'll bring down 2 since we've got our x plus 1 has 2 factors, so we're going to end up with two things. So let's, we're looking at this new polynomial, negative 3x cubed minus 3x squared. Just like when we brought the 4 down up here, we now had the number 64, and we considered how to multiply, or what to multiply 8 by to get to 64. I got to multiply x plus 1 by something to get to negative 3x cubed. So I've got x, so I need to multiply by negative 3x squared. When I multiply that by x, I get negative 3x cubed. Then I multiply by the 1, I get negative 3x squared. Now I'm subtracting. So when I subtract this whole thing, these are both going to become positive. And then I just go straight down. We end up with a 0 again. Then I'm going to subtract 3x, or sorry, bring down my 3x, my negative 3x, and my negative 3. I've got to multiply by negative 3 because negative 3 times x gives me negative 3x. Negative 3 times 1 gives me negative 3. I'm subtracting, so these negatives become positive, and we end up with 0, right? So there's a lot of similarities here in what we did above, and the meaning is going to be fairly similar too, right? There's a couple ways I can think about this. One way is that this thing in our the dividend, that's this big polynomial x to the sixth plus x to the fifth minus 3x squared minus 3x cubed minus 3x squared minus 3x minus 3 is equal to x plus 1 times x to the fifth minus 3x squared minus 3. All right, so I'll let you try the algebra, but if you multiply what's on the right, you'll end up with what's on the left. That's what the division algorithm found for us. What do we, what factor goes with x plus 1 to get this polynomial x to the sixth plus x to the fifth and so on, right? We can also think of it this way, x to the sixth plus x to the fifth minus 3x cubed minus 3x squared minus 3x minus 3 divided by x plus 1 is equal to x to the fifth minus 3x squared minus 3. Okay. Now, this statement's not entirely true because x plus 1 can evaluates to 0 when x is negative 1. And so the expression on the left can't be evaluated at x equals negative 1, whereas the one on the right can be. But with that understanding, right, I can put that off to the side, right? We might look at it this way, for example, when we look at our rational functions and we're trying to figure out how to graph them, this would tell us, for example, if we had this rational function x to the sixth and so on divided by x plus 1, the graph of this would look identical to the graph of x to the fifth minus 3x squared minus 3, except for that hole at negative 1. But we'll dig more into that in other places. Let's do another quick example. Let's now look at taking x cubed plus 7x squared plus 14x plus 3, and I want to try to divide this by x plus 2. Okay, so same game. I need to multiply x by something to get x cubed, so I'm going to start with x squared. So I get x cubed, x squared times x is x cubed, x squared times 2 is 2x squared. Then I'm subtracting, so this becomes negative, this becomes negative. X cubed minus x cubed is 0. 7x squared minus 2x squared is 5x squared. And then we'll bring down our 14x. All right, this comes down there. Now I've got 5x squared and I've got an x, so I'm going to, if I multiply by 5x times x is 5x squared. 5x times 2 is 10x. And again, I'm going to subtract. 5x squared minus 5x squared is 0. 14x minus 10x is 4x. And bring down my 3, right? 3 is coming down. And then I'm going to need to multiply by 4. 4 times x gives me 4x. 4 times 2 gives me 8. Then I'm subtracting. These become negative, and I end up with a negative 5. Right? Now, notice where we're at. We're at negative 5. The game we've been playing is we are looking for numbers to or expressions to multiply x by to get the thing we had, right? So at each step, right? At one point, we looked at x cubed. What do we multiply x by? And that's x squared. And then we had 5x squared, and we multiplied x by 5x to get 5x squared. And then we had 4x, so we multiplied x by 4 to get 4x. We can't multiply x by anything to get negative 5 without having, right, negative 5 over x, but we want to stick in the realm of polynomials here. And so that's not a polynomial anymore. So there isn't any polynomial we can multiply x by that gives us a negative 5. And so we're done. And what we have is a remainder, right? Just like up above when we were dividing 17 by 5, if we're not going into decimals, right? In this case, we're just looking at integer factors, then we're done. There's nowhere else to go. And so let's think about what this means. We can think of this as saying, this result as saying x cubed plus 7x squared plus 14x plus 3 is equal to x plus 2, the thing we divided by, times the result. But then we have a remainder. The thing we have is going to be 5 units too large, and so we have this remainder of 5. Okay? Let's just change perspectives. Again, we can think of this in this way. X squared plus 5x plus 4 minus 5 over x plus 2. Right? This is equivalent to what we wrote here, where we had 17 divided by 5 is 3, but then you have this little extra you have to account for, right? And here, the division leads us to this quadratic, x squared plus 5x plus 4, but it's not quite precisely that. There's this bit extra that we have to account for, this remainder, right? And again, these in this case, we don't have to worry about that 0 thing we did again because it didn't work. The division didn't work out perfectly. These expressions are the same. Both of them have this problem at -2. Neither side can be evaluated there. One thing that this does for us, if we think about rational functions again, and I won't go into a lot of details right now, but if we were starting with the rational function on the left, we could perform division like we just did to rewrite it in the expression I have on the right. And what this tells me is that this rational function looks a bit like x squared plus 5x plus 4. At least it does when x is very large, because when x is very large, this term, excuse me, this term becomes extremely small. For example, if x was 1,000, we would have 5 divided by 1,002. That's a very small number, right? Around 0.005. right? And so that would mean this rational function on the left for x equals 1,000 gives you exactly the same value as the parabola x squared plus 5x plus 4 minus this tiny little decimal, right? So less than 5/1000ths of a difference, right? And obviously, the bigger x get, the less that difference matters. And so this gives you a notion of what the shape of that graph is. Far away from zero, look just like that parabola. Let's take a quick look at the graphs of some of the things we just did. So in that first example, let's go back up here. Oops. That's not what I want. There we go. Let's just look at our results. So I'm going to put these results here. And so after doing the division for this first one, the x to the sixth, here's our function, x to the sixth. X to the sixth plus x to the fifth minus 3x cubed, and so on. One of the ways that I said we could consider that function or think about our result, right, was this as the product of the thing we divided by, the divisor, and the quotient, the thing we got, right? And that's what this is right here. D1, my function D1 over here in Desmos is x plus 1. And then the quotient that I called Q1 is x to the fifth minus 3x squared minus 3. Here's their product. Let's make this a little bolder. Right, so those two graphs are the same. You might be able to slightly, let's make the colors a little different. Let's call this blue. Right, so here's the product of those two things, and here's the original function, right? So we see that we are getting that thing indeed. Here's another graph that might be illuminating. If I take F1 divided by D1, that would be looking at what we did over here, right? Here's the actual division. And our claim is that that's equal to the quotient we got, that x to the fifth minus 3x squared. And in fact, that is the case. So the purple graph is the quotient, and the green graph is what Desmos plots when we divide f1 by d1, that the original polynomial by that divisor. Okay, let's look at our other result. So first, let's start by looking at, here's the original polynomial, x cubed plus 7x squared plus 14x plus 3. And we claim that it can be rewritten as the product of the divisor and the quotient. So let's look at that, but I'm going to ignore the remainder for a moment. So if I put that graph in, notice this orange graph looks the same. Change the color again. It looks the same, but it's not quite there. It's a little bit too high, and so we need to account for it with this remainder. I call the remainder R2. In this case, R2 is just the number -5. We'll see. You'll see examples where the remainder it could be a function, right, a polynomial or something like that. In this case, it's just a constant. But in any event, we see by shifting it down, we now align perfectly, so that we didn't quite have the right thing, but when that little remainder is accounted for, everything works out. So let's now look at it in this second arrangement, where we're thinking about the rational function x cubed plus 7x squared plus 14x plus 3 divided by x plus 2. So here's a graph of that function. Right? So we see we have an asymptote at x equals -2. Let's put that in. Let's make it dotted. A little thinner. All right, so there's our asymptote. And I claim that I can rewrite this function as the quotient plus the remainder divided by the divisor. So the quotient is the result we got, the x squared plus 5x plus 4, minus plus the remainder, which happens to be -5 over x plus 2, right? And so let's graph that. I've got this, oops, turn it on here. So you can just see that it looks like the green graph is just turning red because it's right on top of that. So they are, at least according to Desmos's graph or to the eye, equivalent. And the other thing I want to look at is I noted that this division is showing us, or this way of expressing this division is showing us that this rational function looks like the parabola x squared plus 5x plus 4 for large values of x. So let's put that parabola on this graph. That's our quotient. So this purple graph here. And you can even see at this zoom, where we're not even getting that large of x, the difference is not that much, right? I mean, think about even an x like 10, 5/12 is only about half a unit, right? Or at 5, we're off by, 5 over 5 plus 2, we're off by less than 1, right? So we're already not super far away anyways. And if I zoom out a bit, you can see that our rational function looks a lot like that parabola. Of course, if we zoom in, we will see there's always going to be some gap between them because they are not the same function. They have there's this difference of -5 over x plus 2, but that difference becomes increasingly small as we move further and further away from the origin. In other words, as our x values get larger in either the positive or negative direction. Okay, so I want to just quickly summarize a little bit what we did. We in general, we're taking a polynomial, and we'll call that the dividend, and we'll divide by the divisor, and we will get, when we do this, a quotient and possibly a remainder. I'll just put this down here, right? As we do the algorithm, we might end up with a remainder at the end. We saw in that first example, sometimes they divide perfectly, which tells us that d is a factor of f. A couple of quick conditions. First of all, d of x cannot be 0, right? It can be any polynomial other than the 0 polynomial. We also need that the degree of d of x is less than or equal to the degree of f of x in order for this to work, right? So you're going to be looking for a factor of f of x, or something that's close to a factor of f of x. And then what we have this, what we call the division algorithm, that tells us that under these conditions, we can find, right? So if we start with a polynomial and we have a polynomial d that's not 0 and is degree less than or equal to f, then we can find Q and R, as I showed you in the algorithm, right? The quotient and the remainder, so that f of x is equal to d of x times q of x plus r of x, right? That's just kind of repeating what we did. And it will also be the case that the degree of r is going to be strictly less than the degree of d, right? I'll just put of x in here. It doesn't really matter, right? I guess unless there is the case if they're both constants. So if you divide by a constant and it happens to divide it perfectly, they might both be 0 or degree 0. But in any event, it's just telling us that this is always possible, right? If you have a polynomial and you divide it by a polynomial of lesser or equal to degree, you can always find a q and r to make this true, where r will be of lesser degree than the divisor, right? And we will sometimes use this to think about, this is not the only reason to do this, but one of the things we will do this is to think about rational functions. Right? So we'll rewrite it this way. And notice whenever we do this, because of this condition that the degree of r is less than the degree of d, this term, remember what happens to, this term is a rational function itself, where the degree in the denominator is greater than the degree in the numerator. We know that those rational functions go to 0 as x goes to positive or negative infinity. And so what we're really finding is this thing is like what our rational function looks like for large x, because this term in the box goes to 0. But we'll save the details of that and some practice on that for another thing. That will be it for this one. Thanks, everybody.